In this module, we will discuss what is called as a waveguide. Now, before we go to waveguides, let us just review a couple of points from transmission lines. So, in the last few modules, we have been discussing transmission lines, and most transmission lines have different physical structure. For example, a simple coaxial cable would be made out of two conductors, one an inner conductor and one an outer conductor, right? So they have different radii, and then there is a material that is insulator filled between the two conductors and so on, right? So when you apply a current, so when you hook up this one, you normally ground the outer conductor and then connect a signal source to this one, okay? So when you do that, there will be current going into the inner conductor, and the same current would of course come back onto the outer, from the outer conductor. A different kind of a structure for a transmission line is something that I mentioned, which is called as a microstrip line, right? So in a microstrip line, again you have two conductors, so this would be the first conductor on the top, and then there is also a conductor, right, at the bottom. So this is also a conductor, this is also a conductor. Again, this conductor is quite large, and there is a certain material insulator filling between the two conductors, and we normally ground this particular conductor as well, okay? The most familiar form of transmission line would happen to be a two-wire line, to which you can attach a load and then you can attach a source at one end. This is one conductor and this is another conductor, right? There are additional ways in which you can create transmission lines. So for example, this is something called as a strip line. In a strip line, what happens is that the center conductor that we wrote, okay, in the case of a microstrip, actually lies surrounded by a conductor. It is something like a coaxial cable, but except that it is prepared on a printed circuit board and has a different cross-sectional diameter. Of course, these cross-sections or the diagrams that I have shown here are, the transmission lines are assumed to be uniform in the sense that as you march along the transmission line, so imagine yourself walking down the transmission line and at any point decide to cut the cross-section, transverse cross-section to your direction of the movement, you would see the same cross-section. So these are called as uniform transmission lines, right? Regardless of what was the physical structure of the transmission line, we said that all of these can be described if in terms of a certain distributed circuit, that is a circuit whose resistance, inductance, capacitance and conductance were not at a particular point on the circuit, but they were rather distributed continuously throughout the length of the transmission line, right? So there are ways of calculating R, L, C and G. So for example, we have calculated capacitance for the two-wire line, we have calculated capacitance for the coaxial cable, right? We have also calculated the inductance for the two-wire line, inductance for a coaxial cable and so on. The calculation of R and G are slightly tricky and not really important for our course, and therefore we did not cover that. But they are also related to skin depth, something that we talked about in one of the modules, right? So regardless of what was the transmission line, so these are all different transmission lines, okay? So let me write this as, just to emphasize this, so these are all different transmission lines. All of them were characterized by RLCG. RLCG for different transmission lines would be different, but once you know RLCG, this is the canonical structure that you assumed, right? So this representation of a transmission line by two conducting wires holds for any transmission line whose RL, C and G is known. Why that is so? Because in this piece of wire, if you actually look at a particular region, right, or maybe you should look at this region like this, right? So you imagine that there is an R, there is a series L, then there is a capacitance C and a conductance G, right? So this is your canonical structure for a transmission line. And what was the job of the transmission line? If someone were to ask, well, you connect some source over here and you have a load over there, right? So what is exactly this transmission line doing? What transmission line is actually doing is to convey the source voltage and a certain current, source current, to the load. In other words, it is actually carrying power from source side and then transmitting this power onto the load side, right? So this is actually transmitting power, or power is related to energy, therefore we can think of this transmission line as something that is transmitting energy from one end to the other end. So these are energy transmitting devices. although we have said that these are energy transmitting devices, what really happens is that if you go to the electromagnetic field theory, what you see is that the moment you have some current launched, there will be magnetic fields surrounding this. So the magnetic fields are surrounding like this, right? So don't worry about what direction the magnetic fields are, you can find out that one by the right hand rule. Similarly, for the return current, there would be again magnetic fields, right? So there would be again magnetic fields, and what you can see is that if you call this as the z axis, the length of the transmission line, and let's say vertical down as the x axis, okay, what you see is that the transmission, because the magnetic field lines form a loop, right? So the magnetic field lines effectively come out of this page along the y axis, okay. So the magnetic fields are along the y axis, and for a uniform transmission line, these H lines all lie along y, and they would close around this particular current carrying conductor, okay. So this current is the same current, so I and minus I, so there are these magnetic field lines which are curling around, right. The other thing that you have to notice is that because this is a conductor and this is another conductor separated by some insulator, there would be, and what is current? Current is nothing but flow of charges, right. So there are charges which are flowing, and then so the magnetic field lines will all curl around the current carrying conductor, and there are two conductors for these transmission lines. So one current is going this way and the current is actually coming back. Now if you look at not just the current which is inducing the magnetic field, but current actually is nothing but flow of charges, right, and there is a source that is applying a certain potential, at least at the source end, right. So there is a source which is applying a certain potential difference between two conductors. So you have a top conductor and a bottom conductor, and there is a potential difference applied, which means that this conductor which has abundance of charges will be polarized in two different, or polarized in opposite ways, right. So you have opposite charges. So you have positive charges on one conductor and all the negative charges on the other conductor. The moment you have a positive and negative charges, and remember that these are not just static, they are actually varying with time, because the source potential is not constant and is varying with time. So these are actually time varying potential source or the voltage source that we have applied. So the charge distribution also varies over this transmission line conductors, but the moment there are two charges of opposite polarity, there would be electric field, okay. So you have electric fields down from one conducting wire to the other conducting wire, so let's call that as Ex, and then you have magnetic field, right, that would be along. So I am not going to write down the vector notation because they are not really important over here. The magnetic field line that would be there is mostly confined in that plane that is transverse to both x and z directions. The magnetic field lines are in the direction of Hy. Now an electric field which is directed along x, magnetic field directed along y, both of them varying with time as well as both of them varying with z, correct, because we have seen that the potential on the transmission line or the voltage difference between the conducting plates on the transmission line is not constant, it is actually a function of the length of the transmission line. So where on the transmission line you are situated, that tells you the potential difference between the two. So potential difference, or between the two points on the transmission line is actually dependent on the position of that point where you are taking along the transmission line, okay. So if you imagine yourself walking down the transmission line, what you would see if you carry a voltmeter is that this voltmeter would read different values of the of the potential if the time is constant. So you imagine that time is held constant and you are able to walk along the transmission line with your voltmeter or an oscilloscope. What you would see is that the potential is different at different points on the transmission line, right. So you have since the potential is different, the charge distribution will also be different because current is also changing with time. Both the electric field Ex induced from one conductor to another conductor as well as the magnetic field lines which circulate the current carrying conductor will also be functions of t and z, that is they would also be functions of time and space. And if you now recall that potential difference between say top and bottom is now again function of z as well as t, is given actually from say bottom to top, right, and electric field Ex dx, right. So this is actually the potential difference between the 2 points, whether it is minus or plus, that's a different matter, but the potential difference between two points on a conductor and it is a function of z is line integral of electric field, right. Supposing we had come back to the electrostatic case, okay, so I didn't have a time varying potential source connected to the transmission line. Then if I choose a closed loop, okay, so let's say I choose a closed loop like this and then go around this particular loop, what would I see? I would actually see that the potential at these 2 points is constant, because for the electrostatic case the potential at say points A and B, C and D, okay, so I hope that you are able to see this one. The potential taken around the loop A, B, C, D would actually turn out to be so the electric field line integral A, B, C, D, sorry, again I made a mistake. So this is the loop A, B, C, D that you are taking, and then you are taking the line integral of electric field around this path, okay. This would turn out to be equal to 0, right. So this is a closed path A, B, C, D that we have taken, and then the line integral of the electric field around this closed path will be equal to 0, because electric field from A to B is the same as electric field from C to D, okay, and there is of course no electric field between AD and BC, which also implies that the potential difference between the 2 points A and B is actually equal to the potential difference between the points C and D, and they would also be equal to the potential difference between Q and P. So if you take this as Q and this as P, the potential difference here would be the same as the potential difference at points A, B. So in other words, for the electrostatic scenario, right, the transmission line actually acts like a conductor whose potential is constant throughout its body, so throughout the region. So these form an equipotential conductor or equipotential surface, okay, only in the electrostatic case, but that is not the case we are considering. What we are considering is a time varying scenario. Therefore, for that situation, this loop, line integral over this loop, will actually be non-zero, and this is to be expected, because when you have a time varying potential, right, so electric field is changing with time, this change in electric field must induce a certain magnetic field, right. So from Faraday's law we know that these things would happen. So changing electric field would induce magnetic field, changing magnetic field would induce electric field, and that has to come out. So if in this loop, if you have an electric field which is changing, then there will be magnetic field along y axis, okay, and that magnetic field will be Hy. Then Hy will form a loop, which means that if you take the line integral of H, then that would correspond to a certain current, right, because then integral of H dot dl must be equal to the current, and the current would consist of two components. One, the conducting current on the wires itself, but in the region between there would be a current which is, right, so there would be this current which is called as a displacement current. So what we see in all these things is, to, if I want to summarize this one, is that a transmission line is something that would actually have a electric and magnetic fields present on that because of the time varying potentials and currents that are present on the transmission line, and most importantly this Ex and Hy, which are there on a 2-wire transmission line, and these are the only two components that you can have, or you can have Ey and Hx depending on how you label this axis, and these Ex and Hy are polarized perpendicular, oriented perpendicular to each other. Further, the wave is actually traveling, or the energy is actually traveling along z axis. So which means that you can actually define, or you can describe this Ex, Hy and z as a trio, and these three would actually form the solution of Maxwell equation, wave equation, okay, and Ex and Hy can be thought of as plane waves. So in other words, because Ex and Hy, which are plane waves, they would also correspond to have a corresponding voltage and current, okay, they would induce a voltage and current between the two transmission lines and along the transmission line. They would then be directly proportional to the electric field. So if the electric field is a plane wave, okay, and magnetic field is also the plane wave of the same this one, then the voltage and the currents are also plane waves. Although we never said that voltage and currents, we said that voltage and currents are waves, but we never specified what kind of waves they are, okay. They are of course scalar waves because you are integrating and taking out the vector dependence over here, but the point is that electric and magnetic fields form a plane wave which then induce a voltage and current, okay, and we have been so far analyzing this voltage and the current which comes from integral of H dot dl. So for the space between the transmission lines, this region actually supports a wave which the solution of this wave equation, if you describe that particular region by a wave equation, will turn out to be plane waves. Okay, and energy is actually carried not by the voltage or the current along the transmission line, but rather by these electric and magnetic fields, okay, by the Poynting theorem. So in fact, energy is not transmitted from one point to another point by the transmission line, although its name would suggest that, but rather the transmission line simply acts to guide the electric and magnetic fields in order to carry energy from one point to another point. So in one very broad sense, transmission lines are also guiding structures. These are the structures which guide electromagnetic energy in the form of electric and magnetic fields from one point in space to other point in space. Okay, so if transmission lines are also waveguides, why do we have to study waveguides as a separate module? Why not we simply incorporate whatever we have studied in transmission lines and call that as waveguide theory? Well, there are many reasons for that one. Some of these reasons will become apparent as we go along to the waveguide structure. So although we say transmission lines is actually guiding structure, the difference between the waveguide as traditionally understood and transmission line is this. Transmission lines in the form of coaxial cable, two-wire, PCB transmission lines such as microstrip or strip line, they work only for up to a certain frequency. Okay, beyond that, if you try to make them work, they would offer significant loss and distortion. Okay, there are different cutoff frequencies for each of these different transmission lines, so we don't have to get into that, but anywhere in the range of 3 to 5 gigahertz and above, certainly most of these transmission line structures would not really be guiding energy. Okay, whereas waveguides, okay, are structures which actually conduct very high frequency signals. So they actually conduct signals around, say, from 2 to almost 40, 60 gigahertz. Okay, so these waveguide structures are extensively used to guide really high frequency or microwave signals, and therefore they are quite prevalent in microwave literature. Okay, so in microwave devices you can see waveguides forming, waveguides being used to guide energy. So even waveguides are guiding structure, but there has to be some difference between them apart from the frequency of operation, right? And there is a significant difference. Transmission lines require at least 2 conductors and they support plane waves. Okay, they support plane waves, which means that there is no corresponding Ez, assuming that the transmission line is along Z, and there is no Hz. None of these 2 components exist for plane waves, and these are the ones which are supported by the transmission line. In fact, this plane wave structure is called, a transverse electromagnetic mode. Mode being just a sophisticated jargon for solution of Maxwell's equation. So you solve Maxwell's equation, whatever the electric and magnetic field expressions that you get or the electric and magnetic field values that you get, those are called as modes. Okay, and this particular, plane waves are actually examples of what is called as transverse electromagnetic modes. Why do we call this transverse electromagnetic modes? I have described this in the wave module, because electric field is perpendicular to magnetic field and both are perpendicular to the direction of wave propagation, whereas waveguides are made up of only one conductor. Now how can I make it of only one conductor? Can I just take one ball made up of metal and say this is a waveguide? Well, technically this does not become a waveguide. What it actually becomes is called as a resonator, and we will study resonators sometime later. But with one conductor, okay, for example, if you are able to make a box out of this conductor, right, keep it hollow at both ends and then launch your voltage here. Okay, so you would launch voltage by actually connecting to the conducting plate some voltage source. This would create an electric field and magnetic field, and these electric and magnetic fields are transported from one side to the load side. Okay, so most waveguides, at least the metallic waveguides that I am showing here, would consist of only one conductor. Okay, and this conductor, so why do we say one conductor? Because everything here is made up of only one metal and there is only one conducting continuous conductor out there. Okay, so made out of one conductor, they do not support TEM mode. Okay, there is a small reason why they do not so, we will discuss that one when we really discuss waveguides, but most importantly they actually support higher order modes. Okay, higher order modes simply mean that they have to be waves but not of the same character as plane waves. The defining character of plane waves was that electric field was around, the electric field and magnetic field both did not have a component along the direction of the propagation, okay, that made it TEM mode solutions, and plane waves also had this character that electric field E and magnetic field H in the transverse plane were independent of x and y directions, okay. So you can have plane waves with some dependence of x and y, but the characteristic for TEM is that they should not have Ez equal to 0 and Hz is equal to 0, whereas higher order modes are characterized by having at least one Ez not equal to 0 or Hz not equal to 0 or both, okay. So at least Ez should be non-zero or Hz should be non-zero or both should be non-zero. When do you actually get the situation of both to be non-zero? You actually get that one in what is called as dielectric optical waveguides, okay. So this is another class of waveguiding structures. Here energy is guided not in terms of gigahertz, energy is guided at terahertz. These are the corresponding frequencies for wavelengths which are around say 1550 nanometer, most popular band for optical communication. So the corresponding frequencies are in terahertz, okay, and they cannot use this metallic type of conductors to conduct, okay. You don't actually take a metallic hollow tube and shine light from one side and then expect a light from the other side. You do get that one, but that kind of a distance that is involved with typical optical waveguide such as an optical fiber, you won't be able to obtain from a conductor. Moreover, the operating principles of dielectric optical waveguide is different from that of the metallic waveguides, okay. So the point here is that waveguides would support higher order modes, and these higher order modes, depending on whether they don't have Ez or don't have Hz, are characterized as TE or TM. For TM, Hz is equal to 0, but Ez of course should not be 0. For TE, Hz is not equal to 0, but Ez is equal to 0, okay. These cases where both Ez and Hz are present, which occur in dielectric optical waveguides, are further characterized as HE or EH modes. In the HE modes, H is the one which is dominating. That is, even though Hz is there, the ratio of Hz to Ez is much larger than 1, okay. Whereas for the EH case, the ratio of Ez to Hz is much larger than 1. So it means that Ez is actually quite dominating the mode structure, okay. So we are going to study in the next module, we will start study of waveguides, but the lesson for this particular module which introduces waveguides to you is that transmission lines are also waveguides. They also guide energy from one point to another point, but they are made out of at least two conductors. Because they are made out of two conductors, they do support TEM mode, and pure transmission line modes are only TEM modes. Waveguide would have one conductor, and it would consist of, in a metallic case, it would consist of a hollow tube of metal, okay. The metal could have any cross section. It could have been a rectangular cross section, it could be a circular cross section, it could be a spherical cross section, okay. So it can have a different cross section, but all of it has to be made out of only one conductor, and they do not support TEM modes, but they do support higher order modes. Now before finishing this module, let me just explain to you very briefly why these waveguides would not support a TEM mode. Remember, to support a TEM mode, I need Ex and Hy. And how do I get Hy? Only when I have one conductor which is carrying current along the z direction, okay, or equivalently having, so carrying the current along the z direction, would magnetic field lines around it, okay, and these field lines would then be forming the magnetic fields along y direction, right. So if you space them apart, they would be forming the y direction, y directed magnetic field, okay. So this is very important. For a waveguide, okay, which is say rectangular waveguide, which I am assuming in this particular case, rectangular waveguide does not have any conductor in between, right. So that is obvious, it does not have any conductor, right. So if I were to assume a region of space in between, okay, so if I assume a region of space in between, okay, and it more probably should be something like this. So in the middle of the waveguide, if I assume, and then say I want TEM mode, which means that electric field lines should drop from top conductor point to the bottom conductor, although they are actually of the same conducting thing, but for the magnetic field to be along the HY direction, so this is along the Z direction, this is along the X direction, for the magnetic field lines to come out of this loop, you have this loop that is sitting over here, and for the magnetic fields to form loops inside the region between the waveguides, you need to have a central conductor, right? So a central conductor must be there which is carrying a current so that the magnetic field lines can actually form a loop properly. But this is a waveguide, it has only one conductor. So there is no second conductor here. The moment you introduce a second conductor, these are not the traditional waveguides. Because of the absence of a central conductor, there is no way that you can actually have a magnetic field loop around in any region in between the waveguides. Okay, if you don't have a conventional current, that is all right. You can still have the displacement current, so del E by del T, right? So you can have del Ez by del T, but unfortunately that is also not possible because we have said that this is a plane wave structure, so Ez is actually equal to 0. So because there is no longitudinal current, you cannot have magnetic fields, and because of this reason you cannot have only Ex and Hy components which form the plane wave or which actually form the transverse electric mode structure. Therefore, waveguides do not support a TEM mode. Okay.